Hello, so this is going to be an example of the sort of question you might get about motion graphs. And basically it will be drawing a displacement time graph and then converting it to a velocity time graph. So the example I've got here is a ball that's been dropped and then it's going to bounce on the floor. So the ball initially here is going to start up high, but the velocity is going to equal 0 because it's going to fall down. We've just let go of it. It's not moving yet. As it falls, it's obviously going to get faster. But it's going to get faster in the downward direction. So it's going to be down, and because we've agreed that our convention that up is positive, the velocity is going to get increasingly negative. It's basically going to be that 0 is going to be bigger than the velocity. And then it gets faster and faster, and just before it hits the ground, it's going to be at its maximum velocity, so the velocity is going to be very negative, or much less than 0. Oh, I can't write. The velocity is going to be much less than 0. Then it's going to bounce. And when it bounces, there's going to be a very large acceleration, and then it's going to basically head up almost as fast as it was going down. Now, in an idealised sort of question, it would head up with the same velocity. So if it was just about to hit the floor and it comes down here and it was going, I don't know, 100 metres per second, it would bounce, and then a fraction of a second later it would be going upwards at 100 metres per second. Now, that's not strictly true, and if you think what that would mean is that if you dropped a ball it would carry on bouncing forever. So what's going to happen is that some of the energy would be lost, so it would go up almost as fast. So it would have now a positive velocity, but then as it moves up it's going to slow down, because it's going to be slowed down by gravity, so the velocity will be getting less, so it will be decelerating. So how do we draw that? So it's pretty straightforward really. We'll start with our displacement time graph, very badly drawn, S and T, and we say that we start at the top with 0 velocity, and it's going to get increasingly steep as it gets faster and faster and faster and faster and faster until it hits the ground. Then it bounces and heads up in the opposite direction, so it's going to be heading up now, but almost as fast. So the gradient I'm going to draw next will be in the opposite gradient, so this is negative, it will be a positive gradient, but it'll be almost the same steepness. So I'm going to draw it like this, and then it will get increasingly less steep as it slows down, and eventually at the top of the bounce it would stop. And then this would carry on, sort of boing, boing, boing along here. And that's our displacement time graph. Pretty straightforward. Where this becomes a challenge is translating this into a velocity time graph, because it's not as obvious. Now, you've got two options really. One is you could go all the way back up to this text up here and just sort of work out what's going on and break it down bit by bit. But I think the easiest thing to do is, once you've got a displacement time graph, just remember that the gradient of this line tells you the velocity. So if you estimate what the gradient is at each stage, and you can just transpose that onto your velocity time graph. So, for example, let's start here. At the start here, the gradient is going to be equal to 0. Halfway through the journey, if I worked out the gradient at this point here, Well, it's negative. So the gradient is going to be less than 0. And then just as it hits at the bottom here, that's its very steepest point, it's going to be a lot less than 0. So instantly we know that we've got to plot a velocity time graph that starts with the velocity at 0 and it gets increasingly negative. And you then might have a slight anxiety of, well, yeah, but that could be a curve, it could be a straight line, except we know that it's something that's falling. And if it's falling, it's going to be accelerating down at minus 9.81 meters per second squared. So what we can do for this first stage, and I'm going to shift this piece of paper up, is I'll draw the axes. I've done it too far underneath. I'll draw my axes here, and this can be my velocity, and this can be my time graph, and I'll just follow what it said on the previous graph. So it's just gone off the page, so here we go. It starts at 0. So on my velocity time graph, I'm going to start at 0. It gets increasingly negative, so I'm going to get increasingly negative, and I know that it's a straight line with the steepness equal to minus 9.81 meters per second squared. We then get to the bounce. And we've said after the bounce, I'm going to go back up to this graph here, that, well, it's the same magnitude more or less, but going in the opposite direction. So at this instant here, we're going to have a value that's much, much bigger than 0. And then following on the same logic as before, we get to a point that's just a bit bigger than 0, and then eventually it ends up at 0. At the top of the bounce, it's not moving for a fraction of a second, then it starts falling down. So what's going to happen is that whatever this value of velocity is here, it's suddenly going to jump up to a positive value that's almost the same. So I'm going to jump up to a point up here, and then the gradient gets less and less and less, and the steepness of it is going to be minus 9.81. So my line, and that should line up with that one there. The steepness would be the same, and this would be our graph, except this is weird. We've got a jump between these 2 points. Well, that's the acceleration that the ball experiences as it hits the ground. And it will be a very steep line. In idealised questions, it would be a vertical line, otherwise it would be an almost vertical line. But as you can see, that's a little strange to compare this graph turns into this one as a velocity time graph. So just be ready for them to look strange, and I think it works best if you just look at the gradients and check what the gradient is and map that onto your velocity time graph. There you go.